The buck, the boost, and the buck boost converters that we have looked into so far all used a switch and a diode as their active power semiconductors. Now we can simply replace the diode with a MOSFET as it is shown on this slide here. That means that we, instead of going into discontinuous conduction mode, we can actually conduct current both ways through the MOSFET, and that means that we enable bipolar output. So if we do that for a buck converter, for example, it is actually the exact same circuit diagram as you would use for an audio amplifier or for a motor drive. Our DC-DC converter also turns into a DC-AC converter this way. That doesn't necessarily mean that you have to allow negative output current. You can also put it into discontinuous conduction mode by controlling the switch in a way that it would simply replace the operation of a diode, and you turn it off for rather high current through that diode. We also get lower losses, as the conduction losses in the RDS-on of a MOSFET are typically smaller than what you get from the forward voltage drop of the diode. A disadvantage, especially in low power converters, is that you need an extra gate driver, and if the gate driver losses are a significant amount of your total losses, it might be an overkill to replace the diode with a MOSFET. In case you want the discontinuous conduction mode, you also need to include further detection of the inductor current when it's crossing zero to actually turn off that extra MOSFET. The higher power we are approaching at the output of a converter, the more difficult it might get to get rid of the heat of the losses inside the active power semiconductors. Then it starts to make sense to actually spread out the power across multiple devices and operate a converter in so-called interleave mode. An interleaved buck converter, as shown on this slide here, doubles the amount of power switches used. That could be with synchronous rectification or without. Another advantage is that you can operate those two half bridges consisting of a switch A and B here, and the other one, the switch B and A, 180 degrees out of phase. If we have a look at the gate voltages driving those devices, that means for a duty cycle of 50%, that the derivative of the inductor current of inductor L1 is falling, while the derivative of the inductor current L2 is rising. And that means that furthermore, each of those inductors only needs to conduct half of the output current as its DC current, and that the ripple currents across both of them are canceling out, and the capacitor is ending up with zero ripple. Note that this only holds for the assumption of 50% duty cycle, and the ripple current through the capacitor at the output is still reduced at other duty cycles, but is not equal to zero. We have now walked through the operation of the converters in continuous conduction mode, in boundary conduction mode, and in discontinuous conduction mode. Now it's time to put some numbers on that. For a buck converter that is specified up here with the numbers input voltage, output voltage, operating period time, and the inductance, you are asked to plot the inductor current for an average output current of 5 ampere. After that, the operation of the converter is reduced to a point where the inductor current hits zero exactly at the end of the period. How does the inductor current look like now? And to which value did we have to reduce the resistor that is mimicking the load at the output to achieve that operation point? Furthermore, we increased that resistor once more to reach a peak current of 354 milliamps. How long do we need to conduct the transistor in that buck converter to reach that waveform. And how does the inductor current look like now? And in that third state of operation, what's the average inductor current and what's the load resistance in that case? And here one more simplified converter, in this case a boost converter, in boundary conduction mode. We know that the input voltage is 180 volts, and furthermore, we have the current waveform through the inductor. From only those two information, you can derive the inductance, you can derive the output voltage, and the load resistance. And now for that operating point, you're supposed to redesign the converter to operate the converter at twice the output power, but still remain in boundary conduction mode. What does that mean for the turns of the inductor? Going back to using the original inductance from the first part of the exercise, and now operating the boost converter in interleaved mode with these conduction times for both of the MOSFETs. How does the input current of that converter look like? And what is the maximum and the minimum values of that current? Furthermore, what is the RMS value of the current through the MOSFETs?